Actually, first time for the 10 last years I'm presenting or participating in technical and academic conference. Can you see my screen?
Yes, we see it.
Okay, thanks. Maybe okay, maybe not.
Shift F5.
Yeah, I understand, but okay. One moment. To go to my portion of slides. Okay. My presentation will focus on security in IoT devices, and the first slide shows that with all the good stuff described by my colleague Alexander, the number of connected IoT devices is projected to triple. It's projected to grow from about 13 billions in 2022 to about like 30 billions in 2030. And with all that great opportunity and benefits that we received due to IoT, also great risk comes since the surface of possible attacks increase also with the number of connected devices. And according to the research available on the internet, so why security is important, right? And security in IoT is a growing concern, and reports show that about 1.5 billion attacks on IoT devices in
Or are you showing 24 slide? I still see the title. Oh.
Yes, I'm showing. So some.
Can everyone see the slide 24?
No, I think we better stick to the screen
presentation. Yeah.
Okay.
Yeah.
Can you see now?
Oh, now it's good. Yeah, now it's good.
Okay. Yeah. So report shows that in the first half of 2021 there were 1.5 billion attacks on IoT devices, and the main reason for these attacks is lack of security. Also, according to cybersecurity ventures, they project that a cost of the cybercrime will be like 8 trillion US dollars in 2023. And if just we take this 8 trillions and try to put it in a slower lower time frames, so it's like 255,000 like in a second. That's like a huge amount of losses. And also I like the setup made by Brian Krebs, that if you put on the internet, if what you put on the internet has value, someone will invest time and effort to steal it, right? So it's like really important to protect data. It's really important that data should be confidential, and important to protect assets in this IoT world. And when sensor is connected to the internet, so it's like exposed to the external world, and an attacker or hacker can hack it and get information out of it. And the next question is, so if all this is happening, why is it happening? Why we do not protect our data? Why do not we create like secure devices? And maybe the answer is in the next slide. Like perceptions of technical specialists, it actually differs from reality. And according to PSI security study in 2021, like 3 in 5 tech decision makers believe that their organization like have a good security level. But in reality, only half of the persons that believe that they have adequate security, only half of them perform threat analysis. That actually shows that the perception doesn't meet reality. On the next slide, there is statistic. Okay, if a hack or vulnerability in device causes financial losses, there always is someone that is responsible for these losses, right? And according to the study, 89% of respondents believe that the responsibility is for the chip vendor, device manufacturer, and software or operating system provider. So it's like a huge amount of respondents believe that the problem is actually in hardware, in device, and that's the reason why big companies such as Infineon and other are interested in security. So we need like to protect our devices and our designs. And the companies are interested in deploying the security into manufacturing. And if you take a look at that, it can be divided in three main areas. The first thing is threat modeling, and it's like in simple words, it's if you don't know what you are protected against, how do you know how much security you need? So depending on the devices and their functionality, there are different security levels and different security requirements to those devices, and that needs to be clearly analyzed before we even start designing this device to provide right security level. As a second item, software security is not enough today. And software security need to be accompanied by hardware security mechanism. And the third item is that we need education and we need technical literacy. And so people should be well educated, and there should be awareness about security threats and how to protect against security vulnerabilities. First item is threat modeling in order to mitigate risk. And this diagram presents secure design process. And secure design process always start from identifying all possible threats to a system. And once all the threats are identified, the next step is to identify countermeasures for each of the threat, and then implement countermeasures in secure development environment. And we also have to appropriately secure manufacturing and supply chain. And after all this is done, the last step is to independent evaluation of security. So like that's a third-party companies that provide certification and assign to device some certification level, for example, PSI 1, PSI 2, or common criteria. These two are like the main in the industry. When we perform the threat analysis, we want to answer the following questions. So what are your most valuable assets? By asset, it's like it could be some piece of information, some data stored on a device that has value. What are potential threats to your device? So how can the device be attacked? The next is what types of attacks do you need to protect against? How severe are the threats? What countermeasures could you implement? What your security requirements, and how does your device meet your security requirements? So these are all questions that needs to be answered during threat modeling on the early design stage. The next item is that software, it's not enough to have security device. We need to have built-in security should be built in hardware. And today the security defenses are, so we need strong device identity. That means when device is connected to cloud, it can be identified, and unauthorized devices can connect, or unauthorized devices cannot pretend like to be authorized ones. So this is something that is built really in hardware. Then we have to support like secure authentication, secure communication, secure software firmware update. If a bug is found in firmware and need to update to the next version of firmware to fix the bug, so this update process should be secure. Otherwise, someone may pretend and hijack and insert their own software and get access to the assets stored on device, or get access to the system. The crypto key establishment, boot process protection, and we will focus on that in recent slides and in next slides. And crypto flaws, platform integrity verification, stored data protection, lifecycle management. By lifecycle management, it means like during manufacturing the device is in a manufacturing life cycle, and for example, like debug ports are open, so we can connect the device to debugger and debug our code and program assets to this device. But when the device is shipped, it transitions to production life cycle, and that life cycle states like whether or not the debug port is open. It is controlled by customer policy. If customer wanted to be opened, so it can be opened by. If customer wanted to be closed, that's just configurable. One of the most important security measures, security protection mechanism in hardware is root of trust, or it's usually abbreviated to ROT. And root of trust is a piece of processor where the secure boot starts, and this portion of processor is protected from outside, from non-secure environment, which usually customer application run. And on this diagram, it represents our dual-core architecture. So we can see it has two cores, Cortex M0 Plus and Cortex M4. And Cortex M0 Plus, it serves like root of trust. When the device starts booting, it boots from Cortex M0. And Cortex M0 authenticates the next image that is started on M4. So basically, each image that started after root of trust needs to be identified. And root of trust, of course, it's after that, it's not identified by anything, because it's like first image that starts. And for that reason, this code, it should be placed in either in a ROM, so it can be modified, it's immutable, or in protected flash that also cannot be changed after manufacturing. The next slides present some what is beyond the cryptography for secure boot. So we have a firmware image, and we calculate hash from this firmware image using, for example, like SHA-256. So the result of this operation is fixed with hash digest, and then we sign or encrypt this hash digest with a private key and get image signature. All this encryption process should be performed in secure environment, and usually hardware security module is used for that purpose. Hardware security module is used to generate a pair of keys. Like that's this process uses asymmetric cryptography, and we need a private and a public keys. And private keys is securely stored in hardware security module. It's not exposed outside of HSM. But public key is exposed, and during manufacturing, the public key is injected to the device. This is shown on the next slide, which is verifying digital signature. So the firmware, along with the digital signatures that generated during the previous step, in HSM. The hash of the image is calculated on device, and then this hash digest, the resulted hash digest is compared with the hash digest generated during signature verification process. And for signature verification, the public key is used. And the public key, the only requirements here, so public key can be exposed to anyone. Anyone can know public key. But the important requirement here is that the public key has to be stored with integrity protection. So an attacker should not be able to replace public key with his public key on the device. If that is possible, then attacker can sign the image with his private key and upload this image to the device if attacker can change public key on the device. So public key typically is stored in ROM or in one-time programmable memory. One-time programmable memory is the type of memory when each bit of the information can only be changed from 0 to 1. And once the bit was changed from 0 to 1, it cannot be changed back to 0. So this is works like a security storage for important information and for public keys on device. The problem associated with this approach is that the code that verifies the image, it should be built in ROM. If it should be built in ROM, there should be no bugs in it, right? Because it cannot be easily changed. It can be easily fixed. To solve this problem, the bootloaders are usually divided into several stages. And this is shown on the next slide. Next slide shows that the bootloader is divided into 2 stages. This first stage bootloader and first stage bootloader is stored is immutable. It's typically stored in ROM. It can be changed after device leaves the factory. And typically ACV is integrated circuit vendor, manufacturer, chip manufacturer. And RAM is original equipment. Manufacturer usually represents the parties that produce devices using chips. And customers provides a final application. And so what we see on this diagram is that the first stage boot is immutable, it's stored in ROM, and its functionality is very simple. It just can authenticate the next stage of bootloader. And the next stage of bootloader, it's stored in it's updatable, it's stored in internal flash, and it can be updated anytime it's needed. But the update has to be secure. Before programming new image on device, its identity, it's verified using asymmetric cryptography. So its digital signature is checked before the programming. And customer application can be stored even in external flash, and its customer application is verified using this second stage bootloader, which is much more sophisticated than the first stage bootloader. So this is referred as chain of trust. And the last step, last but not least, is education and technical literacy. And to achieve this goal, there is different materials available on the internet. So on that includes like a security specification, reference implementation, certified API, for example, PSI certified API provided by ARM. They define it like a standardized interface that can be used by different vendors, but it will be compatible irrespective who is the chip manufacturer. Security trainings are available, and also security certification. I mentioned that before, like to achieve some level of security certification, like PSI level 2 or PSI level 3 or common criteria level 4, it's very high level of security. And our company provide solution for each size and for each size and budget. And our devices are certified to different level of security. So when we go to production, we can like select proper device and have appropriate security level. Thank you. That's all that I have.
Thank you very much, Alexander and Oris, for your presentation. Now we have time for discussion. Dear colleagues, welcome for questions and answers.
Alexander is here. Thank you for your presentation, Alexander and Oris. I'm using Infineon in a lot of projects. So first of all, it's great to use your sensors. Apparently, CO2 sensor, the PS family has been really in industrial revolution, I must admit, because we have been working in HVAC with classical sensors, and that was really good. My question is though, is that you can see that the chip shortage is really kicking a lot of product life cycles now. And what I can see is happening is that due to very nice chip vendors facilities, like for instance you shown with the security, vendors actually, or the product owners, they want to step away from that, because if they embed a processor that has all the nice bells and whistles, and then it's not available or has 72 weeks lead time, then people want to have simpler processor, but then push more functionality into software, because they can replace the processor and the product, they can continue selling. How do you see this development in comparison to this very nice all embedded solutions, where first of all you have problems with supply, secondly you might have problems with IP as well, because if it's super smart sensor, then IP belongs to Infineon. If something doesn't work, then what to do?
Okay, thank you, Alexander, for good words and the question. So we mostly on development side, but I can say that from chip shortage, Infineon is in good shape. They have their own factories in different countries, and now just recently was introduced new factory in Dresden for 5 billion. They are opening new factory, so it's like addressing a chip shortage. And from IP standpoint, it's always let's say the problem, and that's why we are working with universities, with different companies, as innovation is very important. So continuous innovation. So you can see from our side, it's just the only method to protect ourselves on the market. And from Infineon, you can see that. Yeah.
Okay, thank you. The second super short question: have you got any kind of PSOC, or maybe the specific parts of the PSOC 6 family support functional safety?
Functional safety, just maybe some blocks, for example, cap sense. Then for functional safety, we are providing all documents, assessment of the quality, so something like that. But it's not like freely available. You need to contact with appropriate responsible people. Yeah.
Okay, thank you very much.
Okay, so
Thank you. Other questions, colleagues? I have one question for Alexander and one for Oris. Alexander, last week at the lecture with my students, we analyzed the case with Tesla accident when in China, when driverless car destroyed a few buildings, killed a few people, and problem with AI-based system on-board system. My question is the following: can we solve such problem or decrease risks of AI related by increasing of number of different sensors on the car board? I mean, we can push, we can locate more sensors on the car, and by processing of information from such sensor, decrease safety related risks.
It's
it's not my suggestion, it's just my thinking. More direct without any additional analysis. Please.
It's very important and very complex maybe question. We are calling this sensor fusion. And like sensor fusion, when you can combine knowledge of different sensors to make some decision. And it's hard to say. So I will be glad to work with you on this area, like how we can improve system reliability, decision making based on sensor fusion. So it's hard to answer. Yeah. So most are trying to put more sensor, but you know that more sensors, it's more errors also and introduced, and it's extremely complex. Yeah.
Yes, thank you. And my question to Orest about more security issues. It was very interesting. Okay, you concerning security of hardware. Yes, because usually this part is not very popular, but very important as I think. My question is the following: what about your experience in application penetration testing for testing and for detecting of hardware and maybe platform vulnerabilities? Yesterday we discussed this problem for robotics system, and it was very close to your presentation. Hence, in your practice, do you apply pen testing, and which features in this area? Is it possible completely to test hardware vulnerabilities? Thank you.
Thanks for the question. That's a really important and very interesting question. Yes, but the answer is yes, we perform penetration testing.
Yes,
and yes. For sure, we do that, and we have like a separate department, even separate group that is responsible for penetration testing, and we have a very sophisticated equipment to do this penetration testing. For example, laser or Röntgen beam, and different kind of like micro probes that you even can like open a chip package and connect to inside the chip and probe the buses between microprocessor and embedded memory on chip. So Infineon is a very serious player on the market related to security, and so we perform all this testing, and we also certify our chips to correspond to certain security levels. So,
Yes.
Sure.
Yes, I've been in your company in Lviv. It's was very interesting trips, and I remember your equipment which you used to test such automotive systems. But now I better understand features of penetration testing for hardware, because equipment can be used to test as usually, yes, but concerning vulnerabilities, there are some specific features and maybe some restrictions to directly test hardware vulnerabilities. And maybe your comment additionally for this.
Yes, and nowadays hardware attacks on chips are very common, and they become cheaper and available to almost everyone. And the time that is required to hack a device is an integral part of any certification. If your device can be hacked, for example, in one day using standard equipment, so there is no security. If your device can be hacked, for example, in 1 month using standard equipment, no security. If your device can be hacked in 1 year, but it's required like very special equipment that cost maybe like $1 million or like several hundreds of dollars. So then there is security in this device.
Thank you very much. Any other questions? I have good possibility for continuing of our joint research and development.
Can I have a question, Slava?
Professor Nikos Bagdis, welcome.
Thank you. Very nice, very interesting presentation, very useful also for all of us. I like to ask you. I saw that you make a verification and authentication through functions and public key of asymmetric algorithms. This is between the servers and the sensors, or between the sensors also? So by the exchanges of information between sensors, also you make this authentication.
Yeah, okay, I see. Thanks for this question. Actually, this asymmetric cryptography that I explained, it was for booting the next stage image. It was not related to secure transfer of the information. I think secure transfer information is performed using symmetric cryptography.
And the authentication that I show, in what level of security you use them?
Do you mean
for what? In which communication you make? Between which?
This is
the symmetric, as I saw. In which level you use them?
We use them when we boot the device. When the device boots, we start from the firmware that is programmed in ROM and is immutable, and the next firmware that is booted on the device is its identity is verified using asymmetric cryptography. So like the next stage of firmware has to be signed with private key, and there is public key on device which is used to authenticate the firmware.
Very nice. And which algorithm you use, if of course it's not a secret, you use standard RSA or something else like elliptic curves or something else? Because it's a computational process that for such a computers.
Yeah, it's used extensive computation process, and we have like dedicated hardware block, IP block, like that this computation performed not in the CPU by software, but by special hardware blocks. And we use both RSA and elliptic curve cryptography. And for RSA, our most recent device used RSA 2045 key lengths, and for elliptic curves we use the CDSI 256. For hash function we use SHA 256.
Oh, very nice, very nice. Thank you very much. Thank you very nice. Thank you.
Thank you. Thank you. Thank you. Any other questions?
I just want to add, Alexander is here, that what Orest and Alexander explained, that's more to Professor Nikos, is that it's a protection from classical problem called jailbreak. When you push the non-signed firmware, and then processor kind of opens up from RAM and allows you to, to get the firmware back from the already flashed product. I think for pin testing, generally, what Vyacheslav Sergeyevich was asking about is it's interesting, and I can see the industry demand on being able to assess products from impersonating data on, in-circuit buses, like, the small ones, I2C, I2S, whatever, the smaller buses where you do not expect any problems to see. And normally during implementation, it's not common to protect those buses because you want to have maximum throughput. So that is rising need, as I see in the industry in general. Thank you.
Yes, and I think
Thank you.
this problem, yes, that you mentioned, yes, that's an important problem, and I believe it's addressing in the way that these buses can only be accessed in non-secure environment, and there is a distinct separation between secure and non-secure. And the interface between secure and non-secure, it cannot be through the external buses. It's only very tight, very clear, and very limited interface. When the non-secure environment sends a request for secure environment to provide some kind of service. Yeah, but that was a great comment. Thank you.
Thank you. Okay, let's thank our industrial partners, our colleagues and friends, Alexander and Orest, for very interesting presentation. And we would like to wish you success in your industry business. And we would like to be safe when we put our car home for our cooperation in the future. Thank you very much. And
if you want the partners in Greece, here we are.
Yeah, thank you.
Thank you.
Have a good job. Yeah.
Okay, thank you.
Thank you. Thank you very much.
Thank you.
Okay, dear